You are welcome to Jonoting online class. In this class, we want to study physics, and the concept we are looking into here is thermodynamics. Of course, on the board we have thermodynamic work. Before we talk about the task on the board, what do we mean by thermodynamics? Of course, it's a branch of physics that deals with heat exchange, heat work, heat transport, then enthalpy, entropy, and the effects of heat. Good. Now, also, terms like internal energy are also concepts in thermodynamics. On the board here, we have a task. We are asked to obtain that work done, that thermodynamic work, is equal to P dV, where P is the pressure and the V stands for change in volume. Then we have an illustrative diagram on the board here. In this figure, we have a system of gas molecules. Of course, when we talk about the system in thermodynamics, we mean matter or group of matter that are separated from other matters around them, either by partitioning or by wall or by a boundary. Now, other matters around the system are the word environment that interact with the system, so that the environment can exchange heat with the system, can do work on the system, and the system can also give out heat or do work on the environment. Good. Now, in this system of gas molecule, we know that gas molecules are always in constant motion, especially when thermally agitated, to have kinetic energy and exact pressure, which is force per unit area as it collides. Now, in this system, these gas molecules are in this gas cylinder, and there is the piston here at one end, and this is assumed to be a frictionless system, so that this cylinder can move freely inward or outward. During the expansion of the gas, it moves outward. Then the piston can be also used to compress the gas, and in that case, doing work on the gas, reducing the volume. Then during expansion, maybe due to thermal agitation by heat supply, which increases the kinetic energy of the molecules, the piston is moved forward. In both cases, force is being exerted, and the gas has pressure. Of course, it involves change in volume, and there's distance moved as per the length of the cylinder. So, having this concept in mind, let us derive this relation. Now, work done, the work is equal to force times x. I want to use x as the distance here, or displacement, which is also equal to f dx in a case of change in position from the original position to other position. But we recall that pressure is equal to force over area. That is force per unit area. Now, when we make force subject to the formula here, we have that force is equal to pressure times area from this simulation. Then, still on this, since force is equal to pressure times area, then we recall that volume. But we have that volume is equal to area times length, or area times height, or area times distance. That will give you what? Volume, depending on the dimension or on the system you are talking about. Now, in our case here, we use S for distance in the change in volume. For that reason, therefore, with this we give us that if we now talk about the V, that is change in volume from V1 to V2 during the expansion, it will now be equal to A dx. That is it. That's area times change in what? Distance or displacement during the expansion or compression. With this now, when we now substitute this formula here, we know that from here, when we substitute these two formulas here now, we'll be able to get the formula for what? Work. Remember that work is F ds, and the F is PA. So substituting this formula now, we now have that W is equals our F is what? PA. equals to PA dx. But our A dx is what? dV. So when we substitute this now, therefore we have that work is equal to P dV. We have that work is equal to P dV. So this is what we have. So when we substitute dV is equal to A dx into work equals to PA dx, we now have that work equals to P dV. Therefore, we say that our work has been proven to be P dV. That is it. In a thermodynamic system, where P is the pressure and V is what? Volume. That dV means change in what? Volume. Analytically, we can equally now say that work is equal to change the integral of P dV, depending on the range of the expansion or compression in the system. Thank you so much for paying attention to this class. With this analysis, I believe you can easily deduce the relation that work is equal to what? P dV, as well as also analyze what we mean by a system and work done in a system or against a system. Now, this has also informed you that we don't only have the mechanical work formula where we say that work equals to force and distance. We can also deduce this relation as work done. For more of these solutions in physics and mathematics, visit my YouTube channel, subscribe, and click the notification button so that you'll be what? Notified each time I upload tutorial videos. Follow me on my Facebook page, all at Jono.